Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's semester 1, 2024, and this is the revision seminar for Probability and Statistics 2, and postgraduate if anyone's here from that class. Okay. Right. So, I should probably save my voice because I've already done a whole revision seminar. Okay, so I might start with the counting. Counting was my favorite bit of year 11 maths, or year 12, or whatever year it was. When I did it, it's fun. Also, my favorite bit of the second year course I did called Discrete Maths 2, which doesn't exist anymore. And that stuff is now in Probability and Statistics 2. And we did more stuff than you did. Yes, and the reason you're given counting is because if you know how many things there are and you choose one of them randomly, you can figure out the probability if you know how many there are. But it's a bit tenuous. But it's fun if you don't have to do it in an exam. And here we are. So, right. Success with counting is, I find, based on knowing, no, before you tell the story. Right. So there'll be some sort of text description of the thing you're trying to count. And it'll tell you whether things count as different or they don't. But one thing that we will tell you about is the features of some objects. You need to know what objects are being described and make that clear in your mind. What objects or collections of objects are being described and what features do they have or not have that put them in or out of the collection that you are counting. So that's very vague, but I'll try and do some examples. But yeah, what objects are you counting? What features put them in or out of the set that you're counting? And then know that you're never counting the objects, you are always counting the stories. Tell a story that says how to find all the objects and count how many stories there are. That may sound like a weird thing to say, but it is how I go about doing counting, and it is what a tree diagram is. Do you know what a tree diagram is? Okay, a tree diagram is a story diagram. It shows all of the stories that could happen. This is a quote from me. Even if you choose not to draw a tree diagram, know that it is probably there in the background anyway. Okay. Right. I am constantly surprised at how few people doing counting problems draw anything. Most humans, even if they don't think they are at least in some way visual. And a picture will help them process. So if you think there is even the slightest chance of a picture helping you process something, then draw one. And probability has one that is well recognized. It's a tree diagram. There's also Venn diagrams, but tree diagrams are what calculates both stories and probabilities. It helps for both counting and for calculating probabilities, either way. Okay. Right. Do I have some examples that I can now show? All right. Okay. So I don't know how to do this without the more complicated things. Happy Meals at McDonald's have three parts. They have a main and a drink and a side. I don't know what they are anymore. When my kids were little, which was, 20 years ago, the mains came in flavors of like the cheeseburger and the pasta, which I know doesn't exist anymore. And it was like a salady thing. I don't know. Anyway, let's just say there's three choices. The main, five choices for drinks, and two choices for sides. And this is like apple pieces or fries, for example. There's probably like 20 drinks because there's all of the soft drinks and then all of the shakes. But I'm just going to go 5 at the moment. And any can go with any. Any can go with any. How many meals? Okay. So you have to tell story. Like the things that are under consideration here are entire Happy Meals. Those are our objects. And they have 3 features, which are mains, drinks, and sides. And each of those features comes in various different types. Okay, so I could draw a tree diagram for this. I do not need to, but I could, and I'm going to. There are 3 choices for mains. And then there are 5 choices for drink. And then there are 2 choices. Oh, wow. I did not do a good job of this. Let me try again. As you can see, they proliferate. Main, drink, side. There are 3 choices for main, 5 choices for drink. This is the entire tree diagram. So this is the start of the story. And you could trace this story in any direction. So maybe they get a cheeseburger and then a Coke and then apples, or they could get whatever this is, the cheeseburger without cheese, and then the Coke again, and then the fries. And every option is here. Every possible story which tells me the things I said to the person at the counter or pressed on the machine at the front is here. And you'll notice that there are 3 paths I could go down, 3 different possibilities. And then each of those has 5 possibilities. So now there's 15. And then each of those has 2. So now there's 30. And this is the multiplication rule. If every option goes with every other option, then you multiply them. But what you are calculating when you multiply them is the branches in the tree diagram. That's the multiplication rule. So the number of meals is 3 times 5 times 2, which is there. And there's nothing stopping you doing it in a different order because everything goes with everything else. But if it turns out that there are rules and you can't have cheeseburgers without fries, then these will not all be the same. And you will have to treat those situations different. So I'm now going to talk about the rules. There are 4 main ways to combine different types of stories. There is the multiplication rule, which we've just seen. So if at stage 2, there are always the same number of options. No matter what happens at stage 1, multiply to get the total. It doesn't matter if the options themselves are different options as long as there's the same number of them. So for example, if you are going to calculate how many ways there are to arrange to choose 3 things and in order from 5 things, no, not paint colors. The classic is ice cream flavors. Choose 3 in order. And the reason they have to be in order is because it matters which one's on the bottom, because the ones above it will leak onto it. And that will change the experience that you have. So choose 3 in order. So there are 5 ice cream flavors to begin with. Step 1, 5 flavors. Let's try and be more systematic about this. Step 1, choose first flavor, which happens in 5 ways. And step 2, no matter which first flavor you chose, there are still 4 flavors to choose from. 3 different ones. So choose second flavor, 4 ways. Now, if you chose chocolate first, then chocolate isn't a choice in the second one. And so if the ones where chocolate is the first flavor, you have different choices than if strawberry was the first flavor, but there's still 4, no matter how many, no matter what you chose. And then step 3, choose the third flavor. And that happens in 3 ways. And since no matter what happens at each step, the same number of ways happen at the next step, regardless of what happens at the previous step, we can multiply. Yay, which is 60. Pretty sure. Yes, because that's 20, and 20 times 3 is 60. Okay. So that's the multiplication rule. And it is very common in this sort of situation. The next rule is the addition rule. If at stage 2, the number of options changes, depending on what happens in stage 1, you're just going to have to separate it into 2 separate problems and add the answers together. If the number of ways changes based on a choice now, you'll have to calculate separately and add. And there's no, I haven't got an example off the top of my head for that, but the idea is that if you've got certain people and some people only go with other people, then it matters which the first person is. So if the first choice you make makes a difference to how many choices there are next time, you'll just have to do the second choice and do all of them and see what happens and add them together afterwards. And that goes with something like this. I'm just going to draw the tree diagram that goes with it. So if your tree diagram looked like this, where at stage 1, there's 2 choices. And then at stage 2, if you're on this one, there's 2, but if you're on this one, there's 3. You can't just multiply. You're going to have to go, well, this one is 2 times 3, and this one is 3 times 3, and then you're going to have to add them. Like that. And the story that you are given will tell you that these stories do this. But I can't think of one at the moment. But yes. What's that? If the number of ways changes based on a choice now, you have to calculate separately and add them. That's the addition rule. I mean, you can always add them even if it doesn't change, but adding a whole lot of things are the same as multiplying. So there's subtraction. So well, one way to calculate the things you want is to calculate all of them and the ones you don't want and take that off. This is similar to improbability of the complement thing. But sometimes it's much easier to count them all because when you have all of them, you can do multiplication. And when you have a specific situation of the ones you don't want, there's only a couple of them, and then you can take them off. So find all of them, find the ones you don't want, and take them off. That's the subtraction rule. And then there is also a division rule, which is if all the ones you want are in there the same number of times, then count them all and divide by how many times they're there, which I call the sheep counting lemma. If you want to know how many sheep you have, and they're all quite tightly packed together and you can't tell where one sheep ends and the next sheep begins because they're fluffy, or woolly if you like. So here's our sheep. Then count how many legs there are and divide by 4, because every sheep has 4 legs. So if you can put, like, deliberately count them all too many times and the same number, and divide. So I'm going to show you this one. This one's really important. It doesn't happen very often, but it's really cool when it does. And oh no, that's okay. So just pointing out, your multiplication rule already says that if you are choosing things in order, and you're not allowed to have the same number, so any of them twice, then you just keep multiplying by fewer and fewer as you go. And that causes the factorial thing to happen. So I'm going to get to that in a second. So there's 2 more things on my list before I get to my examples. So I really should have labeled this page 5. This is page 6. So if you choose choose 3 out of 5 flavors, but it doesn't matter what order you put them in. But in no particular order. So that's much more like you have a bowl, right? Actually, even better from above. Doesn't matter what order they're in, they're all in there. Everyone's touching every other one, so it doesn't matter. The text of your problem will be very clear about whether it's there, whether the order matters or not. And if you are not sure, then you'll just say, I assume that it does or does not matter, so that you can tell the person marking it what your assumption was. So if it's not clear, make an assumption. And if you've got time, make both assumptions and calculate them both. Okay. Oh, crap. Did I actually start the recording? Of course I didn't. No, I did. Yeah. Give me a second. It's probably just given up on me. So here's my, this is using the division rule. I'm going to count them all too many times. I know how many ways there are to count them in order. Count the ordered choices, and we've done that already. It's 5 times 4 times 3, which was 60. And the thing is, if I have a particular 3, if I know how many ways there are to reorder those 3, and they all happen to be reorderable in the same number of ways, then that's sheep with that many legs, and I can divide by that. So count the ordered choices. Given 3 flavors, the number of orders is, well, 3 for the first one, 2 for the next one, 1 for the next one. Because I'm now only choosing from the 3 that I have. And that's 6. And so therefore, the number of unordered ways, so just a second, every collection of 3 unordered flavors has 6 orders in this list. So therefore, the number of ways is 60 divided by 6, which is 10. Now, you're watching very closely. There's a formula now. I don't, in fact, have to do this working every time, but I can if I want. But there's a name for this. This is called 5 choose 3. That's how your lecturer writes it, right? Your calculator probably writes it as 5C3 in your calculator. Or I think R does it as choose brackets 5, 3. Or maybe, oh, I don't know. Anyway. I think in MATLAB it's binomial coefficient 5, 3. Anyway, 5 choose 3 is 10, and it always works this way. What you will have is, all right, bear with me. This here was a number of ways to arrange 3 things when you're going to include all 3 of them in your list. That is 3 factorial. You go all the way down to 1. And so n choose R is always got an R factorial on the bottom. And on the top, it's got n minus 1, all the way down to however many you need to make R of them. R factors. That is how to do n choose R. And it turns out that if you want R factors, well, if you went all the way to the bottom, this bit here would be R minus 1 factorial. And so you end up with n factorial and R factorial, n minus, no, not R minus 1 factorial, but n minus R factorial. But this is a shortcut. This is what it is. So just to be clear, just some examples. 10 choose 4 is 4 times 3 times 2 times 1, 10 times 9 times 8 times 7. It's got, this is 4 factorial on the bottom, and this has the same number of pieces on the top. I don't have to calculate all the factorials involved. There's no need for me to find 6 factorial, because this is the story. I choose them in order, 10, 9, 8, 7, that's choosing them in order. And then each of the unordered things that I want is in the list this many times. And so I divide by that. It's the sheep counting division rule that makes the choose formula work. It's 210. Because, the 4 and the 2 cancels out the 8, and the 3 cancels out one of the 3s from the 9. So 3 times 7 is 21, and 21 times 10 is 10. That is how choose works. There are all these properties of how choose works. For example, 10 choose 6 will be the same answer as 10 choose 4. Because choosing 6 of them is the same as not choosing 4 of them. And so, yay. And so if this is more than halfway, it's probably quicker to convert it into the one that's the other, like these 2 numbers add up to 10, right? So if this is more than halfway, quicker to go to the smaller one and do that. And so choose is one of our shortcuts. So when I had my list of things, there's, yep. So 10 choose n minus, sorry. N choose n minus R is the same as n choose R. Always. Oh, and just be careful, n choose 0 is 1. Which doesn't fit my story, but the act of not choosing is your one way. Yay. And n choose n is also 1. The act of choosing all of them, there's only one way to do that. And look, it still works. N choose 0 is the same as n choose n. and those two things add up to n. So it's cool. And for this reason, we define 0 factorial to be 1, just because it makes all the formulas work. Yay. So just while we're at that, so with our counting, there's a shortcut here with your counting, and it is the choose. And that shortcut is choose R things out of n unordered. And there are different things. Now, this is interesting because when you physically choose them, you have to choose them in a specific order. Like human beings, I mean, you could just scoop them all at once, and that's fine as well. But you can imagine doing this process by taking one out at a time, and that's what this is about. I take one out at a time, and then I just randomly reorder them, and that's what this is about. So, yeah. That's n choose R. And the other shortcut is n factorial, which is the number of ways to rearrange n things. So there are two shortcuts. There is another shortcut, but I don't know if it's in your course or not. There's one where you choose R possibly not different things out of n things. Right. It's choosing no, n to the power of R is n to the R is, yeah, choosing R possibly not different things in an order. Where you just keep having the same list of things to choose from every time. But that's just the multiplication rule. There's n for the first one, and there's n for the second one, there's n for the third one, and there's 5 of them in total, so it's n to the power of 5. So I never have that in my list as a formula because I don't need it, because it matches with the multiplication rule. I can tell that story without needing it. Whereas this is a bit more complicated. That's a difficult story to tell each time. So you have to do the dividing. It's like this. So you can just skip that, do this. There is one way where it goes, well, just a second, where you have an unordered collection of things from n. So you've got n types of thing, and you're choosing R of them, and you're allowed to have more than one of each thing, but it doesn't matter what order they're in. Yes, it's choosing with replacement. Like, no, it's not a permutation. Combinations with replacement. There's I don't know if it's in this course. It is that one. Is that in this course?
Yeah, no, I think it's n plus R plus k choose R.
So choose R, not necessarily different things from n unordered. Yeah. Yep. Yep. Yeah. So this is, or choose n minus 1, doesn't matter. Whichever of them is smaller. So there is a good reason why this is the way it is. It also happens to be minus n choose R, the absolute value of that. So, in case you were wondering. This is just in my head. It's also equal to minus n, the absolute value of minus n choose R. Where minus n choose R is, you've got R factorial on the bottom and minus n, and then minus n minus 1, and then minus n minus 2, and so on. But anyway, so there is a good reason why this is the way it is. And it's to do with very carefully telling the exact right story that produces the things you want. So how would you describe to someone the object that you want here? You would need to say how many of each kind of thing you want. In this one, you say exactly which things you want. And you would have to do that in an order. And so then you divide it by how many ways there are to say that list. And in this one, we're doing the multiplication rule. But in this one, the only way to tell someone what you want would be to tell them how many of each type of thing you have. So like, e.g. A, B, C, and you can have, 5 letters in no particular order. And so this is in some sense, 3 choose 5. Because you're allowed to have more than one of each letter. But it's really complicated. If you try and do a tree diagram for that, you're going, okay, so the first letter could be A, and then the next one could also be A, but then this one could be B, and like A, B, we've already got, oh crap. And it just turns to all these cases you have to add together. But you can do it. The way of telling what you want is just to tell how many A's and how many B's and how many C's you want. You can do that. The thing that distinguishes the different things from each other is how many of each letter there is. And this is why I went all the way back to the beginning. What are the objects that you're counting? You're counting collections of these letters. And what features make those collections different from each other? It's how many of each of these things, each of these letters there are. So a thing that has 4 A's will definitely be different from something that has 3 A's. And a thing that has 4 A's and 2 B's will be different from something that has 4 A's and 1 B. And so it's how many of each letter that tells them apart. Here, that's what I'm about to describe why. Okay, here we go. And even better, if you had someone with a big bucket of A's, B's, and C's, like the letter man in the word market in Dictionopolis in Phantom Tollbooth, you could work your way along your buckets of A's and B's and C's. There's a big bucket of A's and a big bucket of B's and a big bucket of C's. And you could say, please give me one of these. Cool, give me another one. Give me another one. Right, we're going to stop. I'm going to move to the next type of letter. Can you give me one of those? And give me one of those. And maybe we'll move to the next one. That list of instructions, so you can either tell them how many of each letter you want, or give me one, next type of letter of thing, and then so on. You could make a list of these types of instructions. Give me one, next type, give me one, next type, give me one, right? And that list of instructions, depending on where the next type instruction is, will give you different numbers of letters. And so this list of instructions will produce all of the things you want, and each of them differently. And you will notice that you don't need 3 next type instructions, you only need 2. Because you always start with whatever the first one in the list is. You only need to move to the next type of letter twice. And so we have 5, give me one, and 2 next type. And we need to know how many ways are there to arrange those 7 objects. And you know what? It only matters where the next type ones are or where the give me ones are. So I have 7 instructions. Choose 5 of them to be give me one, which is exactly this. The R minus 1 is how many, give me one of these, how many next type of thing. Actually, it's more like this. It's R plus N minus 1. So this is how many, give me one of those. And this one is how many go to the next thing, next bucket. So there you go. That is why it is the way it is. It's like getting a robot with a robot arm to move along the list and pick them out one at a time. So there you go. Some people do this thing called stars and bars, which is the same thing. It's the same thing. But this makes sense to me, giving a list of instructions that will produce the thing you want. Yes. Yeah. And the with order with replacement is n to the power of r, but I haven't put it on my list because I can do that from the times thing. Like that one I can reason out very easily without having to worry about it. And these are the shortcuts of those three things. And it is theoretically possible to construct a story, to construct a set of stories that produces these things, but if you don't want to go through that whole process every time. But this makes sense to me that it's r plus n minus 1, choose r, and this is the number of, give me one of these. And this is the number of next type of thing instructions. Yeah. Yep. Partitioning is a whole other thing. I don't do, was that in this course? Can I number my pages before I say anything else? Okay. That's not a numbered page. Okay, yep. There's not a formula for that. There's a recurrence relation. Oh, all right, I need to see this. Yeah, it's a sum. Oh, no, that's ordering an entire list of things that is made of things that are the same. I don't believe that. Is that what you're talking about? No, I believe it. It's okay. That's just not how I think about it. Okay, we might as well cover it. Might as well cover it. No. It doesn't sound right, but that is how probability and counting works. They call it partitioning, but I was thinking of something else. I was thinking of numbers that, the numbers, how many ways are there to choose numbers that add up to 10, for example? And that's also called partitioning. And so I was mixing it up with a different meaning for the same word. But you were saying you're specifically knowing how many groups, what sizes of groups there are going to be. Okay. Yeah. Split n distinct things into groups of size n1 up to nk, something like that. Is that what we're talking about? Unordered, but you know how many is in each. You know the groups are ordered, but the things aren't ordered within the groups. Yeah. All right. And I know what that is. That's n factorial on n1 factorial, n2 factorial up to nk factorial. That thing. And I know why. Because first you have to choose n1 out of the n to go in the first group. And then you choose n2 out of the ones that are left to go in the next group. And then you just keep doing that, like n minus n1 minus n2, choose n3, and so on until you get to the end. And then there's a 1 at the end because all the last ones go in the last group. But if you look carefully, this is an n factorial on n1 factorial, n minus, yep. And this has an n minus n1 factorial at the top, which cancels with this one. And so on, and then these cancel, and so it all works out in the end to be this. It's also even more straightforward than that. It's the sheep counting lemma. You go, all right, well, I'm going to count them all, which is this. And then the ones in group 1, there's that many ways to rearrange them. And there's that many ways to rearrange the ones in group 2. And any number of ways to any way of rearranging group 1 goes with any way of arranging group 2. So I can multiply those together. So this is a times rule combined with the factorial rule. And then I divide by all of that because that's how many ways everything is there. And so my sheep have this many legs. And so I divide by that. So that's it's really hard to describe on paper. And this is the calculation version of it. Yeah, and if you've only got a couple of them, it's not wrong to just do them in chooses one after the other. If there's only a few. Yeah. Okay. And so this is also the number of ways to rearrange n things when n1 of them are the same and n2 of them are a different type and those are the same and n3 of them are a different type and those are the same. It's the same number of ways. So it's also rearrange n1 things and n2 different things that are same as each other and n3 different things. So it's like n1A's and n2B's and n2C's, and then you make a word out of those. It's the same thing. Wow. But it is all ultimately based at the very bottom on these counting techniques, which were here, these ones. It's ultimately based at the bottom on those. Yeah. Did that help? Okay. The thing that I find remarkable about counting and the way people teach it, I make no claims on the people who are teaching it in this course, purpose of the video, but people teach it as if it's easy, and it kind of is, but it's also really not. And they just say, oh, well, you know, they're this, and then you've got order and unordered, and then there's this table, and you're going, uh-huh. But the key to it is to sit down and think about how would I actually construct all of these things one at a time by giving someone instructions, basically. And that is not basic, but that is usually the way of doing it. And so now that you have choose and factorial, you can actually go, well, I'm going to choose this many. And then in the next stage, I'm going to choose this many. And because it doesn't matter what choice I make here, it makes this, you can actually multiply chooses together as part of the story as well, which is what this one is here that it's gone now. Give me a moment to sort my pages before it gets into a much worse mess than it is currently in. And then we'll talk about something else. Okay? Except if someone has, while I'm sorting my pages, if someone has like a really curly counting example that we could try that bothered them during the course, then please let me know.
I have an example.
Can you just wait for a second? Think about it. All right, it's not in any particular, it's not in the order I said it, but it'll do. That's the other thing with the counting. You actually need to be able to lay it all out next to each other so you can see them all at once and compare them to each other. And so it's not really linear because some of the shortcuts use some of the other rules and then you're allowed to use those again. And so it's not linear, which makes it really hard to figure out how to teach it as a teacher. Right.
I have a question. What sort of methodology is involved when some of the rules that you find in the conditional probability, which also involves multiplication, or conditional probability, which also involves. How do you sort of distill the problem in to its particular elements? And figure out what you do first, and then
So I'm going to repeat that. How do you, and so you're talking probability, which is a related thing. But if you're doing straight up counting, how do you just figure out what order to do it in? And the answer is what I said at the beginning, figure out a story that produces all the things. Possibly involving instructions to another person to do it. And then if you can't figure it out the way your story is told, then try a different story. I know that's such a bit of a cop-out, but you can at least now have these strategies to build together a story that works. I wish I had a good example of one that was hard to figure out. There was one with like taxis going to an airport last year. And there was one with penguins the year before that, but I can't remember the story. I mean, I could do my example. Singing competition TV show has 20 contestants, 5 5 will be in the top 5. Must have Jack and Fatima, since they have the most compelling backstories. How many top 5s are there? So it looks like it was a signing competition. That'd be cool. I wish I knew more Auslan. Anyway. So we have to tell a story that will produce all of the things one step at a time. So I must have Jack and Fatima. So cool, put them in. And there's one way to do that. And now I have to choose. Oh, wait. That's not the question I wanted to ask. That's okay. This turned out to be an easy problem, sorry. But you never know until you get there. And step 2, there's 3 left to choose from the rest of the people, right? Another 3 from the rest. And there's that's 18 people. And there is 18, choose 3 ways to do that. Okay. And that's it. It's just 18, choose 3. Yeah. But yep, go for it. Wait. I'm just gonna get my new page. Okay. 10 passengers on the airport shuttle.
5 hotels. And each passenger gets off at their hotel.
Yeah, everyone gets off at their own hotel, yeah.
Now the actual solution, like setting up the combination wasn't too bad, but the answer was with replacement instead of without replacement, which is very confusing.
Okay. And so we're wondering how many ways are there for passengers to get off, right? That's the total we're looking at, right?
Yeah, possible.
Okay. So there are many ways to think about this, but each person chooses each person before they came off the airport, and like when during their planning, chose a hotel. Yeah. And so the number of hotel choices for my 10 passengers would be 5 to the power of 10, except I'm thinking that our good shuttle driver can't tell any of the people from each other. Right? Yeah. And so from his perspective, he gets to each hotel and says, all right, who's getting off? Right? And then those people get off one at a time. And then he moves to the next hotel. So his story is, so from the bus driver's perspective, person gets off, like as an example of what might happen, person gets off. So like he arrives at hotel 1, right? Person gets off, and then he goes to hotel 2, and then some people get off, and so on, right? That sort of instructions. That's exactly what I was describing before, right? And so from his perspective, what's different is, I mean, he always goes to hotel 1 first before anyone gets off. What's different is when he moves to the different hotels, because even if he has nobody there, he still has to go there to prove to the hotel that he's done his job, right? So what we have is, I'm going to say, I'm going to use this symbol, P for person, and then H for hotel move, right? And so on. And so I have a list of 4 H's and 10 P's in some order. And what distinguishes the lists from each other is the positions of the 4 H's. You tell list apart by position of the 4 H's. And so the number of ways is 14, choose 4. Because you have to choose 4 of the 14 positions to be H's. Is that the answer? That's so not the way they did it?
No, that's, I mean, the answer is not very descriptive on
Ah, okay.
so,
But I have,
it's 5. So that's
oh, there's 5 people.
5.
No, it shouldn't be 14, choose 5. It should be 14, choose 4. Because there's only 4 journeys between one hotel and the next one. I'm pretty sure. I could be wrong. There are 10 people and there are 4 events where he goes to the next hotel. How did they describe it? I'm almost certain it's 14 choose 4. So, I don't think the 5 is you're allocating people to hotels, right? And like the things you're choosing from is always the N, right? You're choosing from 5 hotels with replacement because multiple people can choose the same hotel. And so the N is the number you're choosing from, which is the 5. The N is the number you're choosing, like it should be N plus R, like R plus N minus 1, right? Choose R. And the N is the number of objects you're choosing from with replacement. You're not choosing people with replacement, you're choosing hotels with replacement. And so this should be the 5. You're choosing hotels with replacement, and the thing you're choosing is 10 hotel choices, 1 for each person. And so it's supposed to be a 10 here, not a 5 down the bottom. And 14 choose 10 is the same as 14 choose 4. So it is definitely not, 14 choose 5. The N is the things you're choosing from, and you're choosing from hotels. Because each person makes a choice of a hotel. And this is the number of choices that are made. And there are 10 choices, once for each person. Yeah, okay. And even your lecturer can have trouble with it. It's very difficult to do, which is why I always do it by telling a story of, from the perspective of this person, what is happening and how do I tell those things apart? And maybe that's not what I said at the beginning. Yeah, it's more like I've said what features put them in and out of the set, but it's like what features make it possible to tell them apart. That's what it should be. I'm really glad we're getting into this. This is important. And it would forever plague you as a thing you could never figure out. So I'm glad you asked now.
We're also arguing that, say, we really define that problem we need more.
Yes, we officially had to know that my bus driver is not distinguishing between the different people, because that would be a whole separate problem with a lot more options. If you knew everybody's names and then it's ordered and it's doubly, then there would be 5 out of 10 options for who goes to which hotel. So I think they've tried to imply that the only thing he's interested in is how many people go to each hotel, which is meaning that he can't tell the people apart. But you can always argue that it's ambiguous and say, this was ambiguous to me, and this is the decision I made. So if you're clear about when you said, I'm going to assume that this thing, if you're clear about it, then even if you don't get the whole marks, you might get all but one of them, because they'll go, oh yeah, my question was ambiguous. Or they'll just give you all of them and say, question was ambiguous. Anyone that answered either of these is now correct. Yeah. Gonna extend my singing competition. How many top fives are there? There's that many. Then part B. How many ways could they read out the top five? You know, with the excruciatingly long pause in between each name, right? There are this many ways to choose the top five, which is 18, choose 3. And then you order them, which happens 5 factorial ways because there's 5 names. And so the number of ways is 18, choose 3 times 5 factorial. Choose them first, then arrange them. But there's a whole other way of calculating this, which is choose who the first person is, choose who the second person is. But that's harder. But sometimes the quickest way of getting what you want is to go, well, I'm going to choose them and then I'll arrange them. And even though technically it's the same as just doing the factorial thing originally, sometimes it's quicker. So, yeah.
Of 2 people.
Oh, the 3 here. Yeah, that's why it's 3, because you don't have to choose those 2 people, because there's only you have to choose 2 of them, so there's only 3 people to choose for the top 5. So that's why it's a 3.
That would be effective, but like, if you assume that the bus driver will just be, and then you just get driving, regardless of whether you have people.
Yeah, which is what this is. But even if he doesn't, it still works out the same, because the hotels he goes to are the same order anyway. So even if he's run out of all his people, there's like a secret, the hotels he would have gone to in the list. Yeah. You would have to know when that happened, and yeah, that would be a whole other thing. But yes, that would make it more complicated if it said, what if you were guaranteed that 3 people got on at the 4th hotel, at the 2nd hotel? What would happen then? That would be a whole other thing, and you would probably have to. Oh, we're committed now.
That would be
At hotel number 3. What if 2 people always get on at hotel number 3 and are always going to one of hotel 4 or 5? Well, there's also, yeah, it's 2 different places. It depends on how many people got off at hotel number 1 and hotel number 2. Let's do it hotel number 2. Hotel 3 to 5. It depends on how many people got off at hotel number 1. And so hotel number 1, you could have anything from 0 to 10 people get off there. So there's my tree diagram, right? And then if nobody gets on at gets off at hotel number 1, now we have 12 people that are going to 12 people. Wait. Oh, damn it. We have to know how many people get off at hotel number 2 as well. Okay, so we've got a 2-layered tree diagram here, and then there's, wait, we're nearly there. So suppose H1 people get off at hotel number 1, and H2 people get off at hotel number 2. Yep. Then after that, the number of people left to travel is 10 minus H1 minus H2 plus 2, right? Yep. and they have to go to 3 hotels. Hotel 3, 4, and 5. And we know how many ways there are to do that. The number of ways to do that is this. There's this many people. And this many journeys to the next hotel left to go. And we have to choose 2 out of my list to be the journeys to the next hotel, which is the same as choosing how many people choices there are. Like there's this, yeah. Officially it's this, right? Right. There's this many choices to be made. There's n 3 minus 1, like there's 3 hotels to choose from, and we're going to make this many choices, which is the same as 14 minus h1 minus h2, choose 2, and then we have to add all of them up for all the possible choices of h1 and h2. Yeah? So we're going to have the sum, because they're all different choices, right? So we have to add them together. They're different stories. So we're going to use our addition rule. The sum from h1 to, which is 0 to 10, and then the sum from h2, which goes from 0 up to 10 minus h1, 14 minus h1 minus h2, choose 2. That is the answer. Not that I know what that adds up to, but that is definitely the answer. Yay!
So it's some the 2 independent events that come.
Yeah.
The hotels and the people.
No, I'm summing these 2 sums are coming from how many people get off at the first hotel, how many people get off at the second hotel, and then this is all the choices that happen after that. And so what I'm thinking about is I've got a tree diagram, and each of them has fewer options, right? Because if everybody gets off at the first hotel, it's just finished there. So each of them has fewer options for what happens. And then each of these has a formula for what it is. So that is an answer. It's not a good answer, but it is an answer. And so I'm using the addition rule here and the how many ways are there, choosing with replacement rule here. Yay! I'm impressed myself there. I have to say that was impressive. Feeling all right? If I were a lecturer, I would so have that question and say, express as a sum the answer so that you don't have to figure it out. Oh. But I have to say, kudos to everyone for coming up with what if questions that make to say, what other questions could we try and answer? Always good to do a what if. Okay. That was all counting, but I'm good. Like if you're good, and Maths Learning Centre is open for the next couple of weeks, so you can always talk about anything else. But we've got half an hour to go, and so what are we going to talk about? Infinite Markov chains, plus on process.
Don't make it about fight. If I can make it 5. Yeah.
And they were just, in my opinion. It was like 2 pages of stuff.
Would you like me to go through one of those examples from scratch? Because I don't have any other. The easiest way to do this is with an example, I think. So let's answer that question. What do we mean by infinite Markov chain? It means a Markov chain with infinitely many possible states it could be in. The number of possible states is infinite. So a traditional Markov chain's only got like 3 or 4 states. But an infinite Markov chain for example, it could be that it transitions from how many people have a disease from one step to the next, for example. And so theoretically, we never know how many people there are going to be in the world in the future, so it could be infinite. It could also be how many seconds are left until the washing machine finishes, you know, and it's giving you washing machine time units, and you never know for sure whether they're really minutes or not.
Never trust the washing machine timer. Never trust it.
Okay.
Just one question. And the work he did, I basically copied it word for word. You can see it here.
Okay, so this is from the 2024 week 11. What is this? The workshop?
Yeah.
Random walk on the non-negative integers. Okay. So at a given time point, Gordon, I'm just putting the most important information here. So assume that a given time point, Gordon is in an integer I, which is greater than or equal to 1, then the probability, okay, so if at integer I greater than or equal to 1, the probability that we go forward to I plus 1 is 1/5, and probability we go backward to I minus 1 is 3/5, and that leaves the probability of staying in I to be 1/5. Probability stay at I is also 1/5. And if at 0, probability of go forward to 1 is 3/5, and the probability that we stay at 0 is 2/5. Okay, and then we let xn be this current state. Yep, be the position at time n. And that is a Markov chain. So that's our story that we have here. And the questions we've been asked are state space, transition probabilities, equilibrium equations, and equilibrium distribution using recurrence. They're the instructions. Okay. Hold up, sorry. So the method they're using here to do this used to be in discrete maths too, 20 years ago. Maybe someone hasn't caught up with the fact that that's new information for you now. Anyway, all right, here we go. My state space is 0, 1, 2, 3, etc. forever. It might start at 5 or something. Yeah, it might only be the even numbers. Okay. So with a traditional Markov chain, most of the Markov chains you'd seen up to this point, the state space is just 0, 1, 2, 3 or something like that. Okay, transition probabilities. They have told us explicitly what the transition probabilities are. So in order to, when they say what are the transition probabilities, that must mean they want a particular notation, because otherwise you can just say, well, you told me. Here they are. And so I'm pretty sure that they want something like Pij or something like that. But we can't do a matrix because there's infinitely many choices for what the state could be. That's the problem. If they were finite, we could just write a matrix and that would be the transition probabilities. But there's infinitely many of them, so we can't do that. So we do know, just writing down what they've told us, is that for I greater than or equal to 1, Pij plus 1 is 1/5. Pij minus 1 is 3/5. And Pij is also 1/5. If I read that correctly. Yep. So in general, he's moving back more often than he moves forwards. Our game player here, that's useful to know. And then also, presumably Pij is 0 for all other j. I don't know if you have to say that, but I'm putting it in anyway, just to be absolutely certain that I have covered all my bases. Okay, and then for I equals 0, P0, 1 is 3/5, and P0, 0 is 2/5, and P0j is 0 for all of the j. This seems like a comprehensive list of all of the transition probabilities to me. Does that feel good? Feel right? Yeah. And we can draw a picture of this if we want. There's 0, and there's 1, and the probability of going here is 3/5, and the probability of going here is 2/5. And then here's 1 and 2. The probability of going here is 1/5. Probability of going here is 3/5. The probability of going here is also 1/5. And then every one of them is the same as that. It's 1/5 this way and 3/5 this way, and staying here is 1/5, and then they're all the same, right? Forever. And we're very lucky. Well, they've been nice to us by making sure that we don't have ones that skip 2 back at the same time, because that would make our diagram really complicated. So, yay them. Thank you. Okay, and the next stage is the equilibrium equations. So equilibrium means in this setting, because there's only one person doing this game, we wait for a random amount of time, and we don't know how long we've been waiting for, and then we look at where our game player is, and we say, what are the probabilities of them being in a particular spot? We wait for a very long time. And we say, where is our person? What's probably being there? Or we could imagine it as 10 million people all playing this game simultaneously. And then at any moment we can look at it and go, and then like we wait for like a long time and then go, where is everybody? What percentage of people are in each of the states? That's the other way of thinking about it. Both are okay. They're both, I mean, yeah, probability. So if you're doing only got one person, you're comparing it to all the other paths that he could have taken. So there's always 10 million Gordons walking them numbers. Okay, so here's the thing: if you have 10 million Gordons on the game, if you're at the equilibrium probabilities, even though every Gordon, they all move simultaneously at every turn of the game, after they've all moved, it looks the same. So some of them move forward, some of them move back, some of them stay where they are. but the ones that come back are the same, are equally matched with the ones that leave and go elsewhere. So the ones that come in are equally matched with the ones that go out. And so the equilibrium probabilities are, yeah, that's the thing.
As long as none of them leave the game.
Correct, as long as none of them leave the game. And there is no way of leaving this game because it goes forever and you don't jump off the game at 0. And in that case, you would just count leaving the game as one of the states. You just add it to the number of states. Okay, so the probability, the equilibrium probabilities are called pi, not p, because it's Greek for p. In fact, that's how you say the word pi in Greek. It's p. You know that. We had a long conversation about this. Right, so the transition probability is like pi I is the equilibrium probability of being on the number I. Okay? So there is always one of them that is definitely true, which is the sum of all the i's, of all the pi's has to be 1. Because it has to be somewhere, and so the probability of being somewhere is 1. Okay, that is our first and always our first thing. Okay. So, well, they put it as the last one, but I put it as the first one because it's always true. Okay. And that is an infinite sum, and that's going to be a thing. We'll get there. And the other thing we know is that the probability of being on this spot, like here we are at position 10 billion of the game, and we have a probability of being in position I. I'll just do it for position I first, for I greater than or equal to 1. We have a probability of being in position I, and we know that the 1/5 of those Gordons will move forward to 2. Yep. And cool, we'll move forward to I plus 1, and they won't be there anymore. Okay, and 1/5 of these will stay in position I, and 3/5 of the ones that are from the next one up. So we're going to say the ones that arrive in this spot, where are they coming from? Some of them come from here. So that's 1/5 of the ones that are already there. 3/5 of the ones that are here come here. And oh no, position 1's going to be different. Damn it, this is I is greater than or equal to 2. Sorry. I is greater than or equal to 2. 3/5 are coming back from I plus 1. 1/5 is coming from here, and 1/5 is coming forwards from I minus 1. So 1/5 of the one, this is how many, this is the percentage that's in position 1, and 1/5 of those come forward to here. This is the percentage that are in position 3, and 3/5 of those are coming back to here. And this is the percentage that are in position 2, and 1/5 of those are coming to here. And that's supposed to work out to the same percentage after all. In your notes here, it says, this is the sum of j, pi j, p j 1. Like, this is the sum of the being in position j and the probability of going from j to I. Officially. But all the ones that it can't get to from there aren't in this equation. So this is what this is. So this is saying that the probability of being in position I is the probability of being in any other position times the probability of getting to that position. It's kind of this weird-ass tree diagram. So we're going to jump, kind of like we're going to jump direct to pi 0, pi 1, pi 2, pi 3. And then there's all these ways of getting to various places. And we only want the ones that get to position I. Yeah. And so this is the P0I, and this is the P1I, and this is the P2I, and so on. So it's like a big tree diagram, but what we're doing is we're not starting at the very beginning of the game, we're starting at the end of the game when it's already gotten transitioned. Like it's already gone equilibrium. Okay, so this is an idea in my head, but for this particular game, this is this. 1/5 of the ones that are in I and 3/5 of the ones that are in I plus 1 and 1/5 of the ones that are in I minus 1, they will all arrive here in I, and that will be the same as what we started with. We okay with that? And then for I equals 1, here we are at 1. I'll have 3/5 of the ones at 0. And 1/5 and 3/5 of the ones at 2. And 1/5 of the ones at 1. Sorry, they're not in the right order. That's just how I'm reading the diagram today. 3/5 of the ones at 0, that's this bit. 3/5 of the ones at 2, that's this bit. And 1/5 of the ones at 1 stay here. It is very common at the beginning to have different ones. And finally, when I equals 0, bugs. When I equals 0, we've got 3/5 of the ones at 0. 2/5, sorry, of the ones at 0. And 3/5 of the ones at 1 is pi 0. Sorry. 2/5 of the ones at 0 and 3/5 of the ones at 1 is pi 0. So these are our equilibrium equations. This one, these infinitely many, and these two. They are our equilibrium equations.
Like a lot of rearranging.
I mean, there will be rearranging, I'm sure.
Yeah, but like rearranging.
Well, we have 4 equations. We have infinitely many equations, technically, and infinitely many unknowns. But yes, 4 equations and 3 unknowns is probably a useful way of thinking about it, because it's basically the same thing.
Would it always be that an I0 is equal to pi 0 and so on?
What do you mean?
So that I equals 1, that the sum of both pi is equal.
Yes, because this one was equal to pi I, and this one's equal to pi 1, this is equal to pi 0. The lecturer wrote it the other way around with this at the front. But in my head, it's like this has happened, and then it turns out to be the same answer as we came from. Like, it makes more sense in my timeline in my head. But anyway, and for my tree diagram, it makes more sense. But anyway, that's fine. You can put them on whatever order you want. So you could theoretically rearrange this to figure out that pi I is equal to something, because there's pi I on both sides here. So pi I is on both of these, is here and here. So you could rearrange this to get pi I equals something. Yeah, but I'm not sure how to move from this point. Apparently, things that have linear equations like this, a power of some number is an appropriate thing to guess for reasons that I don't know what they are. It was a long time ago that I did discrete maths too. But it's very similar to differential equations. Certain kinds of equations have certain expectations based on the wisdom of those who have trod this path before us that we should try. And so, and also, if it really is a power of something, then this will be a power series, it will be a geometric series, and I'll be able to figure out what the answer is. So that would be nice. That would be nice. So there'll be some weirdnesses going on at the beginning, but then there'll be some stuff at the end. They should all be behaving the same at the far end of this. Yeah. So we're going to run with this one. And the late letter here is related to, wait. So, gonna be weird stuff going on at the beginning. But out there, far into the line, what happens at 0 is not going to really make much of a difference overall. And so I'm going to look at this one and see what happens. So I'm just going to go back to this equation from the I greater than or equal to 2 equation. I'm going to rearrange it to have the latest value of I. Sure. Going to rearrange. This is the way it works in my head. I'm sorry. I'm going to have the latest value of I, which is I plus 1. I'm just going to write this down again. 1/5 of pi I plus 3/5 of pi I plus 1 plus 1/5 of pi I minus 1 is pi I. So you don't, I mean, you've got choices. You can rearrange it. So we can rearrange it to get pi I plus 1 equals. That might be nice. You'll notice here that you can figure out pi I plus 1 from pi I and pi I minus 1. And so because it's a two-step recurrence relation, you expect there to be two different answers. In the same way as a second-order differential equation has two different answers. It's like it's extremely analogous. So we're just going to try it and hope that it works. Try pi I is something to the power of I. That is our hope. It is our hope that this is true based on the wisdom of those who came before us. Our mathematical ancestors have tried this and it works, so shall we. You must find happiness where you are. And so that means that pi I plus 1 is m to the I plus 1, and pi I minus 1 is m to the I minus 1. M is for some number, not necessarily an integer, probably not an integer. For some m greater than 0. And it is probably a fraction because it's a probability. Yeah, it's a probability, right? In fact, yeah, you're right. For some m between 0 and 1. Because it can't be a probability unless m is between 0 and 1. Yeah, good thinking. Feeling good about that. And so this is great. 1/5 of m to the I plus 3/5 of m to the I plus 1 plus 1/5 of m to the I minus 1 is m to the I. And all of these share an m to the power of I minus 1. Divide by m to the I minus 1, which we can do because m is not 0. Because we said it was strictly between 0 and 1. Yeah. And so this would leave me with 1/5 of m squared. No, just m, that one. This one would be 3/5 of m squared. And this one would be 1/5 of m. No, that'd just be 1/5. And this one is m. Yeah, and it's a quadratic. I'll multiply everything by 5. And 3m squared minus 4m plus 1 equals 0, which is a perfectly good quadratic, which will give me two answers, as I said there would be. Oh, cool. Like that. 3m squared minus 3m minus m plus 1. Yeah, there we go. Or you could use the quadratic formula or whatever, complete the square. So 3m equals 1, 4m equals 1. And so m equals 1/3. Yes. They divided through by the 3 as well and managed to factorize it with the 3rd in there. Fun times, fun times. Therefore, expect all solutions to be pi I equals something times 1/3 to the I plus something times 1 to the I. So whatever these two numbers are, you stick them in. You knew it was something to the I, and you do a linear combination of them, because these are linear difference equations. And that is how they work, because the solutions are subspace. Yep, we expect all the solutions to be that. And then what we're going to do is we're going to sub it into everything else and see what happens. So this came from all of these equations. It came from all of these ones simultaneously. And so we'll sub it into all the others and hope. So let's see. Let's get our I equals 1 equation. Actually, can I do the I equals 0 equation first? And the reason I'm doing that is this one only involves 2 numbers, whereas this one involves 3. So that one's going to be a little easier to cope with if I sub it into that one first. So the I equals 0 equation is that 2/5 of pi 0 plus 3/5 of pi 1 equals pi 0. And so if I subtract 2/5 of pi 0 from both sides, I'll get 3/5 of, oh, look at that. So pi 1 equals pi 0. That's fascinating. That's not where the, oh yeah. And so that produces that. And so pi 1 is supposed to be a times 1/3 to the 1 plus b, because b, I to the 1 to the I is just b, is just 1. And this is a times 1/3 to the 0 plus b, and the b's cancel, and that's not distressing at all. And so a would have to be 0, but if a was 0, then all the probabilities would be 1, and that's impossible. No, they can't all be the same, because there's infinitely many of them. What did the lecturer do?
The probabilities were just like, well,
What this tells me is that the equation, the formula doesn't work at I equals 0 and or I equals 1. Yep. Okay, cool. We're not going to do this because we don't know if it works at I equals 1 or 0. So we can't use that equation at those places. Right. So I really do have to use fascinating. Okay. Bear with me, I'm just thinking. We do know, this bit's still true, right? This bit here is still definitely true, right? We know that. Yep. Pi of 0 is definitely equal to pi equals 1. So that's not false. But this bit here, that's okay. This bit is not okay. Okay, we do know that pi 1 and pi 0 are the same. And from I equals 1, we know that 3/5 of pi 0 plus 3/5 of pi 2 plus 1/5 of pi 1 is equal to pi 1. And we know that pi 0 is the same as pi 1. Cool. So we've got, that's pi 1. Maybe we should do it as pi 0, hey? Nah, pi 1, because the other ones are already pi 1. And so we've got 3/5 of pi 1 plus 1/5 of pi 1 is 4/5 of pi 1. And so 3/5 of pi 2 is equal to 1/5 of pi 1. And so therefore pi 2 is 1/3 of pi 1. Or pi 1 is 1/3 of pi 2, whatever. Ah. Right. That's getting us somewhere because we know what pi 2 is because it works when I is 2, this formula. The formula back here that we got works when I is 2. Because that's where it came from. Yeah. Nice. And so doing okay. So we've got that pi I, for I greater than or equal to 2, pi I is a 1/3 to the I plus b. And we know that pi 1 is 1/3 of pi 2, which is a. Is that helpful? I don't know if that's helpful. And we also have that pi 1 equals pi 0. Yep. This is what we've got so far. Right. And we have one final equation that we haven't used yet, which is the sum of all of these things is 1. There are. There are indeed infinitely many. Okay, so I'm just going to go, when I is 0, we've just got pi 0. Yep. And when I is 1, we've got pi 1, which is the same as pi 0. And then for the rest of the i's, it's a 1/3 to the I plus b. Yep. And infinitely many b's added together is going to be infinity unless b is 0. Like, no, I really should have done what I did before. Damn it. I'm just going to do it. This is 1/3 of a times 1/3 squared plus b, right? Because that's what pi 2 is. Yes, you do. Mm. I get 3 pi 2 equals pi 1 back here. Have I done something wrong?
Then you say pi 1 equals 1/3.
Oh, yes, you're right. So pi 1 is just 3 pi 2. Cool. Thank you. The world makes sense again. So that's a times 1/3 plus 3b, yeah? And we multiply that by 3. Oh, that's making more sense. Cool. I'm just going to stick them all in exactly as they are. So this is a times 1/3 plus b, and this is a times 1/3 plus b, like that. And this cannot be equal to 1, like, so this is 2/3 of a plus 2b plus the sum from I equals 1 to infinity of a times 1/3 I. I'm going to bring this a out. Plus the sum from I equals 1 to infinity of b. And that definitely, that will not come out to 1 if B is anything other than 0, because this doesn't exist if B is not 0, and so therefore B is 0. Okay, we've got a good start there. And so now we've got 2/3 of A plus A times the sum from I equals 1 to infinity of 1/3 to the I is 1. And the sum from I equals 1 to infinity of 1/3 to the power of I is off by 1 from what I want it to be. I'll just bring out a third so that it actually starts at 0. Is that okay? I've removed one of these thirds, so there's all the powers are now 1 less than they were before. And there's a formula for this. 1 over 1 minus a third. That is a geometric series. So I've got 2/3 of A plus, now 3 times that would be a half. Two-thirds plus a half. Past 1 6/5. No, 7/6. Actually, just put them over 6, David. Don't try and be clever. So A times 7/6 is 1, and so therefore A is 6/7. And so therefore, pi 0 is A is, which was A times 1/3 plus B, which is 0. And so that's now 1/3 times 6/7. Sorry, I should do it in the order it is. 6/7 times 1/3 plus 0, which is 2/7. Pi of 1 is also 2/7. And then pi I is 6/7 times 1/3 to the I plus 0. That is it for I greater than or equal to 2.
How about that?
I don't know. My instinct is that your lecturer will get you to set up the equations but not solve them. Or set up the equations for you and ask you to solve them. So, but I reckon the setting up of the equations is probably, this is my theory, the setting up of the equations is probably more important to your lecturer than the solving of them. It is my instinct. But yeah, but I can't be sure. But you know, because I don't know what's in your lecturer's head, but I'm pretty sure. So there were some moves there that I just want to make sure that we take note of, and that the whole year until I do this again, or maybe next week, you know. You use the recurrence relation from the point where it started, which was I equals 2. That's when the formula started to work. And that made this true for that greater than or equal to 2. You need to use the other equations to be able to figure out what the earlier pi's are in terms of these. So I got those equations and I got to here and I could write them in terms of the capital A and B as well. Oh, this one was a 3B here, damn it. Not that it matters. Oh, no, even better, 6. Right, that's better. And then you can sub it all in and there will be some infinite sum reasoning that allows you to figure stuff out. But it is extremely important, do not sub in the earlier i's that are not involved in that first equation that started when I is 2. Don't sub the earlier i's into that because it doesn't work there. It only works where that formula works and those earlier i's don't work. So you will have to figure them out in terms of the first I that works, which is 2, and see where you go from there. Poor. Wow.
I equals two, under the summation notation, like.
Yes, that's an I equals 2 there, because that's when that formula starts to work. And this is me thinking I equals 1, I equals 0 and I equals 1, pulling them off the front of that sum. Oh no, I've said here it was 1. Have I done everything? Oh, damn it. This started at 2, and then I've said it starts at 1, but it actually starts at 2. So everything's different. Damn me. That's a 2. That makes that a squared. And that's a whole different thing. 9 minus 3 is 6. And 2/3 plus a 1/6 is 3/4. No, it's not. It's not at all. It's 5/6. I'm distressed by that because that would be 6/5, but that's okay. That's okay. It's allowed to be more than 1 because the 1/3 makes it smaller. 6/5, that's a 5, that's a 5, that's a 5. They're all 5s. Okay. Okay. Cool. We should just check that. We're currently up to 4/5. This is going to need to be 1/5 when I add all of them together. And, oh yeah, cool. Yep, because we know that the sum of all this thing here, we just did that back there, it comes out to 1/6, so that's okay. Okay, cool, everything works, it's fine. This is the answer you're looking for. Was that a worthwhile thing to do? Well, I did look at the solutions and I disagreed with them.
So they get the pi out, yeah. And then substitute in at that point, the pi is a 35 one. It's fine.
Oh, they found the b equals 0 from that bit. Yeah, that's a possibility too. Pi2 is 1/3 of pi1. Yeah, so what they did is they went to, how did they get that? I have now lost all the pages. Just a second. Right, that's definitely the first page. That's the state page. That's space. That's definitely the second page. And then that's definitely the third page. If you times everything by 5 here, you get 3 pi2. Yep, the pi2 equals 1/3 of pi1 is where I got it. They had to sub in the previous one though to get that. Like that pi0 equals pi1. Like, yeah, I've replaced that pi0 with pi1. Like they've used these two equations just here together to get that one. And they've said it's by BC2, but it's actually by BC2 and 1. Because pi2 is 1/3 of pi1 is where we got, right? Ah, yeah. So I guess you can do it in any order, but you do have to fiddle with those two little equations and make them equal to whatever the first one in the series is. 3. And then that's page 4. And then that's page 5. And then that's page 6. Okay. So we've got equal chances of being at 0 and 1, and then less and less chance of being at all the rest of the numbers. Okay. But not impossible. Yeah, when you add all of these things together, you'll get 1. Because this series converges to 1/5. All right, I will stop now because we are now a long way over. Thank you for watching. If you're watching in the future at this last final stage,